Ishibashi, President at the Nagasaka Corporation, and Ken Miyashi, Engineering Director at Nikken Saki.
Hello, I'm Hiroshi Ishibashi, President of Nagasaka Corporation and Ishibashi Foundation. I represent the co-owners of the Museum Tower Kyobashi in Tokyo, and I wish to thank you for giving me this wonderful and exceptional opportunity to introduce to you what we have accomplished.
Hello everyone, I'm Ken Miyoshi. I'm the Engineering Director of Nikken Sekkei, mechanical engineer for this project. We are very honored and excited to be part of this event. We would like to present our achievement for our Museum Tower Kyobashi from here in Tokyo, Japan.
Museum Tower Kyobashi is a skyscraper of approximately 150 meters in height, and my two organizations share the 23-story building. A high-grade leasing space for business offices occupies the upper two-thirds of the building and is managed by Nagasaka Corporation. The lower one-third is occupied by Artisan Museum, one of the top art museums of the French and Japanese masterpieces in the country. The museum space is managed by Ishibashi Foundation. The history of the piece of land on which the building stands today goes back to 1939, when Shojiro Ishibashi, the founder of Bridgestone Tire Company Limited, purchased it before he moved the company's head office from Kurume on the island of Kyushu to Tokyo. The location is ideal even today, as Kyobashi district is very close to the Tokyo station, which is the focal point of extensive railroad network in the nation. Kyobashi is a mainly business district, and an excellent access to nearby retail and cultural districts is available through Central Avenue. Other large-scale urban redevelopments have been proceeding in the area in recent years. Now I must talk briefly about the founder and my grandfather Shojiro Ishibashi. Shojiro was a real entrepreneur who expanded a small family footwear business to create Japan's top tire maker by the 1960s, and he did so by vigorously pursuing developing the technology, which was solely based on Japanese engineering. He naturally had a great interest in the latest technology for his tire-making business, but he was also keen on modern architectural technology, which would enhance the company's productivity by providing comfort and safety to the office employees. In 1950, Shojiro Ishibashi visited the United States on business, and he was greatly inspired by what he saw in modern Western buildings of the time, such as the headquarters of the United Nations. In 1951, he completed the construction of the new head office building in Kyobashi, which adopted several new architectural technologies and used cutting-edge materials of the time. The 9-story American-style building was one of the first high-rise architectures to appear in the post-war Japan and quickly became a hot subject in the industry. Here are some examples of new features introduced in the building. I understand this was the first building to adopt fluorescent light in Japan. Aside from being a successful businessman, Shojiro was also a true philanthropist. He was greatly inspired by art museums, which were thriving with people in American cities. So at the last moment, he decided to install a gallery in the new office building and opened Bridgestone Museum of Art, the predecessor of today's Artisan Museum. For him, his dedication to the culture in the society was a passionate personal mission, and he donated his entire art collection to the museum and founded Ishibashi Foundation in 1956 to manage it. Throughout his life, he built or financially supported to build a total of 4 art museums, including 2 national museums. Shojiro also founded Nagasaka Corporation and provided the best business environment for the organizations he managed. The new Museum Tower Kyobashi was jointly built by Nagasaka Corporation and Ishibashi Foundation on this land where our history and tradition lived. The old building went through many phases of renovation during its existence, and this is the most recent view before it was demolished in 2015. In 2012, 60 years had passed since its construction. A decision was made to rebuild the architecture from the ground. In the wake of the big earthquake and tsunami of the previous year in 2011, our main focus was on disaster prevention and business continuity. When we embarked on the project in 2012, we decided to inherit the founder's philosophy as our DNA. We made it a goal to achieve an advanced architectural system using the best technology available at the time. Personally, I am an industrial designer, and it was my turn to complete an architecture with a high level of balance in design and function, which will survive through the future. Compartmentalized coexistence of the museum and the business zones was a prerequisite. To achieve our goal, we consigned Nikken Sekkei Group to furnish the best solution, which I hope to be a landmark in architectural design. Thank you. And now Mr. Miyoshi will speak to you.
Thank you, Mr. Ishibashi. Now from here, I would like to explain our achievement on the project related to MEP design. Before I go into the details of the project, I would like to talk about the background in short. As mentioned earlier by Mr. Ishibashi, our unfortunate experience of 3/11 certainly was a warning bell to remind that we should never underestimate the power of natural disaster. The scale of earthquake was shocking, but what has even threatened us more was the secondary catastrophe of a nuclear power plant. Tokyo has experienced brownouts in rotation of area. The event has forced us to remind the importance of resiliency, and at the same time, we thought about the right direction moving forward in terms of energy use. Tokyo is still one of the busiest cities around the world. When I started to work as an engineer 20 years back, some still believe that the beauty of office workers was to be busy and stay until the last train of the day. Early 2010, the negative side effects of unfavorable labor situation became social issues, which made the government to restrict such labor style. This also encouraged employers to supply comfortable and productive work environment rather than space just for desks. Of course, beyond city scale, but rather global scale, there is a still major problem that we all need to seriously consider. Corresponding to these three keywords, high-rise buildings in Japan have focused on achieving high performance mainly by implementing latest technology associated with active components. These, of course, was the requirement for our project as well. At the same time, the project team, including our client and architect, thought that there is a need for connection to the environment, which believe it will create the breakthrough for the further improvement. As most of you may know, Tokyo has a significant change of 4 seasons. Especially spring and autumn time, you can feel the comfortable breeze and daylight, even if you are in the middle of Tokyo. We find that there are less reasons to isolate the indoor environment, yet we tend to forget this valuable potential. Oftentimes, implementing passive measures to high-rise buildings may not be understood as the first priority and may not be easy as to those implemented to low-rise. For example, operable windows for natural ventilation is a nice-to-have feature, but instantly people may become concerned about negative impact, such as rain, noise, polluted air, etc. We have taken serious integrated design process and made solutions to those concerns point by point. The goal was to achieve high performance, which in this project have put many efforts to make connection to the environment by integrating passive and active components. From here, I would like to explain some of the major features of the tower. First, green. It is said that when you are in high elevation, you may feel greater estrangement from nature. At the rooftop, skip floor green garden is created as part of biophilic feature. Office workers can experience both indirectly from the indoor as well as directly by stepping outside. Here is the green garden at the top floor. It is open as semi-public space to all the office workers within the building. we have conducted post-completion investigation on the effect to the workers' performance and resulted that there is certainly a positive effect to comfort and productivity. Next feature is the light and view. Like other buildings around the world with hot climates, maximizing daylight and view is a trade-off with solar heat gain. Without compromising the cooling load, the typical office floor have achieved with every orientation to have glazing for introducing daylight and views. This, we believe, is a value that not degenerate and promises the long life of the building. This cannot be achieved only by high-performance glazing, but as seen here, the tower is protected by aluminum louvers in all orientation. The louvers are arranged in different discrete patterns, depending on the orientation of the building. This pattern was designed by utilizing computational approach with various simulation to allow filtered natural light and maintain views while protecting from sunlight. As you can see, even without any artificial lighting system, the space is bright enough during daytime. In addition, the artificial lighting system was developed to enhance the environment. Foo value, which is the newly developed index to express sense of brightness, was utilized for the design. Having high ceiling as this office could have been a disadvantage if the lighting system was designed in a traditional method. However, by introducing sense of brightness method, the LED lighting fixtures was designed to maximize the Foo level, maintaining brightness of the surface of the ceiling. This resulted to limit the lighting power density at maximum of only 5 watts per square meters, while maintaining Foo level to 25.8. Of course, in addition, daylight and motion sensors are installed to reduce even further. Now I would like to move on to today's main topic, ventilation. For high-rise buildings, it is widely regarded as impossible to apply natural ventilation using wind pressure through the facade due to the difficulty of high pressure control. But this building challenged the development of the hybrid ventilation system and proved that it is very effective under local climate conditions in Tokyo. The natural ventilation system for our project uses both wind and stack pressure in a complementary fashion. The intent was to maximize the effect period and mitigate fluctuation caused by weather conditions for stabilized ventilation. The stack effect is created by double skin configuration at east and west side facade. The double skin was extended 30 to 40 meters up to the crown part in order to create negative pressure to draw the air from the indoor, even on the higher office floors. It is estimated that approximately 30% of annual HVAC system operation hours are available for wind ventilation. In addition, stack effect expands the effective period by an additional 3% during the hours with low winds. The outdoor air temperature range between 15 to 26 degrees C is considered to be the best condition for natural ventilation. Especially for the low side, intake air may become uncomfortable when diffused into space directly. To mitigate this concern, diffusers of the recirculation VRF units were allocated adjacent to those for outdoor air intake. In this way, the effective period of natural ventilation is further expanded. Here are some pictures of the inlet and outlet openings for natural ventilation from workspace. You can see that diffusers for recirculation system at the perimeter, as I mentioned earlier. It is estimated that this natural ventilation system can reduce the annual cooling load and contribute to approximately 5.7% of energy saving against the baseline model. The effect of natural ventilation was not only estimated during the design, but also post-completion measurement was conducted by support of Professor Kurabuchi from Tokyo University of Science. As you may imagine, verification for such dynamic system is not straightforward. Measurements mainly by pressure, air velocity, air movement, and tracer gas density was conducted during October 2019. The ventilation rate were measured ranging from 1.8 to 3.1 air changes per hour, with an efficiency of approximately 0.5. The result was equivalent to assumption made during the design and also equivalent to the ventilation rate regularly designed for mechanical system. The measurement also proven the effect of stack effect by the double skin facade. As shown here, the exhaust air volume transition is following the sun path, where you have greater volume on east side during the morning time, whereas the exhaust at the west side becomes larger in the afternoon. For the mechanical system as part of integrated active components, the office floors are equipped with DOS with water source VRF, which are zoned in small area within each floor. In this way, the system can conform with various diverse work style while minimizing the energy used for the tenants. Micro-DOAS, a very small dedicated outdoor air system supplying only 650 cmH, was developed and integrated with the facade. It consists of high-efficient EC fans and is located between the columns at the north and south perimeter. The control is designed to automatically optimize the ventilation mode of demand control, airside economizer, and natural ventilation hybrid mode. It is estimated to contribute to the reduction of water-air conveyance energy by more than 30% compared to a traditional central DOAS system. Underfloor air distribution was introduced to effectively distribute from the system, especially in heater season. Taking advantage of outdoor temperature difference, mainly caused by absorption of direct solar radiation at the south side and shading at the north, the direction of the outdoor air intake is automatically switched to further minimize the load. In summer, lower temperature air is taken from the north and vice versa in winter. The result of post-completion measurement shows the significant effect as temperature difference of 5 degrees was achieved during the peak summer and 7 degrees C during the peak winter. As explained earlier, water source VRF system was adopted for heating and cooling, which minimizes the thermal conveyance energy and allows optimal control according to the various usage. The supply air from the VRF indoor unit is distributed through the overhead soffit, which have identical form to the structural beams. The soffit act as a radiation panel for improvement of operative temperature, in addition to effect by underfloor distribution system mentioned earlier. This realizes within minimum amount of customized and rather just with combination of commonly available systems. Since humidity is mainly controlled by micro-DOAS, VRS control was adjusted to maintain high sensible heat operation, which results in high efficient operation and avoid condensation risks. Integrated design process has realized a ceiling of 4.2 meters, which is significantly high compared to standard offices in Japan. We believe this will create multiple benefits from small controls to flexibility of usage in the expected lifetime of the building. We also think that the space and hybrid ventilation system is also contributing to mitigate the risk from the very difficult situation of pandemic that we are all facing today. Based on the local simulation method EUI for the whole building, it is estimated approximately 1,200 megajoule per square meter per year on a source basis. The baseline model was approximately 1,800. Thus, this project is expected to yield energy savings of 30% or more. The actual measured energy consumption for the first year after completion was 1,400. While many reasons can be considered for this, one of the major reasons is the fact that the demand control ventilation was disabled for the intent to maximize the flow rate as part of pandemic prevention. Also, we have to admit that the initial year after completion is presumed to be reflecting a lack of tuning for actual usage and conditions. Currently, monthly commissioning meetings referring to various operation data, including those presented today, are held for improvements. We think that this PDCA cycle after completion is a very important process to truly realize the high-performance building. High-rise buildings are a large-scale project which I think has a significant social responsibility. I believe the retransition of design by creating buildings that is connected to the environment rather than to isolate from the outside will improve performance. I hope the challenge addressed here have added value to the project and provide a real-world solution for future high-rise projects, especially in high-density urban areas. Thank you. that brings the presentation to an end. Thank you very much for listening, and I hope you have some felt the atmosphere of this building in middle of Tokyo.